Hello. So I'm working at Nokia Berlin. I'm a software engineer. My name is Tomasz Dobrowolski. And I wanted to tell you about our 3D Maps product that is already live on maps.nokia.com/webgl. So before we had a plugin. It's already also online. And with the plugin there is a problem that if you go on a web page with a plugin, you see some text, you're almost there, you have to click to install, you have to wait, reload, and so on. And it always bothers users, and sometimes they are refusing to accept something or install. So this is the main reason why we actually plan to switch to WebGL. So we have a beta web page on maps.nokia.com/webgl where you can just type in the address and you have a WebGL capable browser. You are just in a 3D world already. And this is not a surprise, it is written 100% in JavaScript. What else? And I can tell you some story how it started. So we have started 1 year ago, and I made an early prototype actually in February 2011 because I didn't believe it's possible to make in JavaScript such large-scale rendering and application. And actually the very first prototype turns out to be successful, and it worked, and not so bad performance. Yeah, so even me didn't believe it's possible, but it was. So then we started to progressively add more features, and this is quite surprising because at the beginning we had one complete city working in 3D, but we added globe later. So it turns out that rendering a city might be easier than full globe. And then when we had all the cities and the globe, we decided to make a first public release, beta, in November 2011. And then now you can experience also terrain, 3D terrain outside the cities. And we released that with the terrain on April at Where2.0 conference. So what features we have so far? First, you can explore the world. This is the major use case, and get familiar with a place before going there. For example, if you go to Berlin, you probably want to see some tourist attractions or famous places like Deutsche Bundestag. And you can see the Deutsche Bundestag from different angles, see how the entrance look, what is in front. Also get more details now with HTML5 overlays on top of WebGL, on top of 3D. What you can also do, we added search, so you can search for a restaurant and discover, for example, using 3D view, the restaurant with the best view. So for example, if you go to Cape Town on vacation and you're looking from very good restaurant on a top of Table Mountain, and you want a beautiful view on a coast and other mountains, then you can find it using our maps. And last but not least is actually my favorite feature. We added stereoscopic 3D experience. So as you can see, I highlighted the glasses that are in the top right corner. If you click on these glasses and have red-blue glasses, you can explore the city in true 3D. This is probably the first 3D maps that offers that kind of feature in a browser. And we are quite proud of it, and I think the results are quite amazing. So I would just quickly show you some of the features, because how it works in real time, right? Sorry. Forgot about internet connection. Could be helpful. So let's wait for a while. So I would like to now tell you a bit how we are doing it, what is behind the scenes, what is rendering technology we are using. But first I will show you some features I will be talking about. You don't see it, of course. Okay. So you see, it's a standard WebGL capable browser. We have a globe level with atmosphere, some nice shader. We also added, as I mentioned, terrain. So let's go to Alps, for example. You can explore Alps in 60 frames per second. Then you can go to a city. Let's go to Madrid, for example. And you can see this is working not bad, actually. So, thank you. And yeah, then you can enable for stereoscopic view, right? And it's still working not bad, even rendering twice. So now let's go back and I will close this. How we are doing it, right? So this is not surprise. We are using tile-based rendering approach, as most of the mapping technologies. And we are using Mercator addressing scheme, so we map square Mercator domain on a sphere, right? So you don't have North Pole and South Pole, but then you have very nice square tiles at every level of detail. And as you can see, we map for the globe a square satellite image on some area on the globe, and the same for the higher level of detail. And we go on with the quad tree subdivision and increased level of detail. So, but what is the difference? If we go to the city level, actually, we switch to 3D geometric tiles. The concept is very the same. That's why, actually, it's quite uniform approach for the terrain, for city, and for the flat globe. Geometric 3D tiles are also square from the top, and we also, as you can see, even cut through the buildings to make it possible. And they are also in Mercator addressing scheme. So there's not really much difference, and we have also level of detail. So here mesh, this is lower resolution mesh with lower resolution textures, and this is a bit higher resolution. And we go on and render these tiles. So how the general rendering overview, how does it work? It's really a simplified overview, I have to mention. But first of all, we put somewhere camera, and we have to decide which tiles are visible in the view, right? And then, of course, some tiles might be already in GPU. Some tiles might be missing, and even not in main memory, because we didn't download it. So then we have to make a request, download these missing tiles, and then when they are downloaded, upload to GPU, right? And then again, the next frame, let's say, if everything is there, we can render. This is a general overview. And what we discovered very early, that rendering was not a bottleneck. So as someone already mentioned, this GIS applications deal with huge amount of data. This is also no different. And yeah, the bottleneck is handling this huge amount of data. So what kind of data we are talking about? What kind of magnitude? So compressed on the server, we have per city 20 to 65 gigabyte of data. This is texture plus meshes. And when it comes to the client, so you can imagine you have to download. Of course, you don't download whole city, you only download visible tiles. But if you make per view some measurements, and you store this data uncompressed already in a GPU, and it's roughly 10 times more to handle than in standard 2D maps with tie approach. This is actually quite a lot. So you have to upload to GPU, imagine just for one view, 120 megabytes, and organize all the streaming smoothly, and that was a lot of effort to make it working nicely. So what we quickly found out that WebGL and JavaScript, it's quite limited platform still. You have to rely what browser provides you, the API, the compression, and so on. So we came up with its term WebGL friendly data format, and this is what we use for all kind of data we are using for rendering, also for meshes, for terrain, for textures. So then we compress this data on the server without any compromise, that I will also mention later. And so really heavily compressed. So for example, textures are even compressed up to 5% of original size using JPEG and some tricks. And for meshes and for the terrain, it's not so good compression because we are using gzip. This is what browser decompress for you and so on. So we didn't have much choice. We could use some better like 7-zip or whatever, but browser doesn't provide you, and this is not WebGL friendly, right? So then we, again, as I told, rely on a browser to decompress everything and directly upload to GPU. So for example, mesh data is actually what we compress is raw index and vertex buffers without any kind of encoding. So we just browser decompress it for you, and we just push it to upload to GPU as it is, without any copying or processing. So then how it looks on a more like complicated picture. So what is happening behind the scene? You have a browser thread, JavaScript thread, and WebGL. And this is the beauty of WebGL architecture, that they separated rendering thread from JavaScript and browser thread, right, from processing. So as you know, there is this command buffer in between. So JavaScript is just generating commands that are pushed to some kind of queue and then executed by WebGL rendering thread. And to be honest, JavaScript is here usually the biggest bottleneck. That's why we wanted to minimize this processing. And browser is in parallel, hopefully, doing the compression for you. So I would explain a usual cycle. What happens? Of course, you have this animation frame callback. Everyone uses now on animation frame. And then usually in between, because there is only one execution thread in JavaScript, right? In between, there is some callbacks on load for request happening, right? So what happens first, this is setup when we decide which tiles are missing, which tiles are visible, and then we issue some requests for the missing tiles, for example. Then we have render step when we render what is not missing, what we can render on the view. And then, that is quite upside down, we actually upload what was requested cycle before, right? So upload all this mesh data, index buffers, and textures to GPU, and we really do it slowly. So we don't upload like full everything we have in a buffer. We really stream it to keep constant frame rate. And actually, as you know, to make it in 60 frames per second, you have only 16 millisecond frame window to do everything. And then, of course, when the browser receives this request and decompress for you the gzip and JPEG, then we have some small decoding part that is happening on load callback. And this is, as I mentioned, we try to make it as fast as possible to not use any JavaScript processing. And on the rendering thread, on the other side, everything works, should work, we should keep rendering thread busy, right? Put as much data as GPU can handle. So then you can nicely balance the stream and get the best performance. So yeah, we managed to do it. So what will be the wish list? I would like to start maybe later some kind of discussion. What do you think about the future of WebGL and so on? And I think texture compression would help a lot. And it's, of course, I know in this recent browsers like Canary and I know this development builds of Google Chrome and so on, there is already some texture compression working. But I think the problem is still not solved. I think also there was some presentations from Google about that. The problem is what to store on a server side. If you store on a server side just, I don't know, ETC1, well, what is, as I believe, currently going into standard, then, for example, if you have a platform that supports PVRTC, then you have some kind of problem, right? You have to convert. And also, ETC1 on a server side and PVRTC, even compressed, can still be not as compact as JPEG. So as I mentioned, we have nice tricks for making JPEG compression, and we achieve even 5% of original size. And I try all these other tools, and there is no way to beat JPEG. So I think the problem is still not solved, and would be nice to have some native JPEG depends on the platform, or maybe some different new format. So this is one thing. And another thing, which is about my favorite feature, I would like to have full support for 3D screens in every browser. Which means, of course, it mostly depends on the hardware manufacturers like NVIDIA, which is probably hint for them to do something with it, because usually it's not the fault of the browser developer, but it would be really nice, because so far we have red-blue glasses support, and we are rendering just twice with color mask and so on, but even that experience is very good. I think it's much better with real 3D screens and real 3D glasses. This is what we are looking for in the future. And then I invite you to maps.nokia.com/webgl, and maybe there are some questions. So thank you.
We have time for questions.
That's a very, very, very impressive demo. I think, right? Do you use the same renderer for both the globe and the city views, or do you switch renderers?
No, it's the same. What do you mean, switch?
I was wondering if you had used a different model, if you had a separate model for the cities, or if the cities are actually placed on the globe model. So
the rendering architecture is pretty uniform. So we have tile-based approach in Mercator scheme. We are traversing the tree, Mercator, and actually switching just to different data sets. So this is, of course, this is different procedure for drawing all this data set, but more or less it's some common architecture on top.
And a follow-up question to that, do you have any precision problems with only 32-bit floats in WebGL and a large globe model?
Yeah, that we are using for matrices. We are using native. Not native, this JavaScript arrays. Even float 64 array, should be okay. But of course, with these tricks to you know, don't lose precision while multiplying matrices through camera and so on. So it all applies, of course. You cannot make it working without it.
Question: how do you create the level of detail models for the buildings? What kind of mesh reduction are you using?
Yeah, this is not our job, to be honest. So I'm responsible for developing rendering, and I know there's some texture atlas and some you know, probably some standard mesh decimation with some kind of error, but it's not my part. Sorry.
Okay, any more questions? Wait, please use the microphone.
Excuse me?
What is the effort that it takes to make these textures in 3D?
You mean prepare the data set or to render?
Preparing, shooting by aerial flybys, or
Yes. So all I can say that we have some third-party companies that we are getting this data from, and they are using airplanes, flying around the cities and collecting data. But it's quite an effort. Yeah, this is probably also the hardest part of.
Okay, last question.
So that was amazing demo, really.
Thank
So do you have any plans to make this work on Windows phones, on your Nokia phones?
So
because
I can show you something behind the scenes, but not on the Windows phone actually. But but I cannot announce anything. I agreed with that with Nokia, so I'm sorry. No, I cannot say anything about this.
Okay, thank you again very much. And
Thank you.